let's continue. So what we have done so far was that, so again, we want to solve indexing with k mismatches. So we are designing this data structure, and for the time being, k equals 1, but we will generalize to larger values of k in a few minutes. And we said that first we check that whether there is an exact match. So we have this compacted trie storing all the strings. We start at the root, we navigate, and we find the first node u where we get stuck. And possibly u is a leaf. In such case, we have an exact match, but maybe we don't, and then we have to do something more. And we have said that we look at this heavy path decomposition of this compacted trie, and we have possibly many edges on the path from u to the root, where we should have followed another edge. So we have followed a particular edge because that was the next character in our pattern, but maybe the mismatch is right there and we should have followed a different edge. Okay, that was the setting. And we have done more or less the case when this mismatch is at node, is an edge v prime, where this edge is a light edge. Okay, so this is what we have done. I have all those edges on the path from u to the root. There could be many of them. And some of them are the heavy edges, and some of them are the light edges. And we have shown that you can consider efficiently all other possibilities. When instead of following a light edge, you follow a different light edge. Okay? Did it make sense? How we have done that? Should I recap? Maybe let me recap. So we say that first of all, there are just log n of those light edges. So there are the number of places where we should have followed, where we could have followed a different light edge is just logarithmic. Yeah? And in each of them, we would like to check all the other light tridwen. So we have followed an edge leading to v prime, but we say, but maybe we should have gone to another light child. So we would like to have all those other light tridwen. Yeah, we would like to take all those green subtrees, and we would like to have a merge of all of them. And in the merge, we would just follow with the remaining part of the pattern, and that would give us an answer to a pattern matching with one mismatch query, assuming that the mismatch is at that position in the pattern. Okay, if we can, if we do have a merge of all those green subtrees, so all the light tridwen of v, but except for v prime. Okay, that makes sense, what we have done. And then we had this simple trick. So we said that instead of, so we would like to store the merge of all those green trees, and that might be space consuming. So we have said that we build this binary hierarchy of tridwen of V. Yeah, so those are all the tridwen of V. You could think that V is here. And for each node in this binary decomposition of the tridwen of V, we store the merge of all the corresponding tridwen. And then when you that doesn't take too much space, because again each leaf in the original compacted trie corresponds to log n times log sigma nodes in those compacted tries. One log n comes from the heavy path decomposition, and log sigma comes from this binary hierarchy. Yeah, so each of those leaves contributes at every level in this binary decomposition. And in the query time, we take v prime. We follow the path from v prime to the root in this binary decomposition, and we take all the edges that hang off from this path. And in each of them, we have stored the merge of the corresponding tridwen. Okay, that makes sense so far. What we are doing, more or less, at least on the high level. So okay, so now we would like to do something similar. Now we need to do two things. First of all, I want to show you here the space is n log n times log sigma. Yeah, one log n from the heavy paths, and log sigma because of this binary hierarchy that we built, this segment tree or whatever is the name that you want to. And I promised a single log, so I need to keep my promise. That's one issue. And another issue is that we have processed the case when the mismatch is at a light edge. That was the case, yeah. But the mismatch could be also at a heavy edge, and most probably there are many more of them. There are many more heavy paths, heavy edges on the path than light edges, yeah, because there are only log n light edges. Okay, so those are the two issues. So which one do you want to solve first?
The first one.
The first one. Good choice. Okay. So let's try to decrease this to n log n. So what's the intuition? The intuition is that the way that we have chosen this binary hierarchy, it's kind of oblivious to the sizes of the subtrees. It means that we take all the children of V and we pair them, and then we group them into pairs of pairs, and so on and so forth. And this is completely oblivious to the sizes of those subtrees. Yeah, it's like a very simple partitioning that doesn't take the sizes of the subtrees into the account. Okay? But maybe one of those subtrees is very large. I mean, they're all light children of V, so they cannot be too large. But one of them might be larger than the others. Okay? So think about one of those trees being kind of large and the others are not so large. Okay? So then, when you think about it, I mean, how much do you pay in the space? Each subtree contributes its size at each level of this binary decomposition. Yeah, so this large subtree contributes at log sigma levels. But does it really have to contribute at all levels? Maybe you could partition the children a little bit differently. So that so again, that's the way the special case that we are thinking about is that there is one subtree which is much larger than the others. Okay, and still we have chosen this binary partition so that all of them contribute log sigma times. Okay, but one of them is much larger than the others. Okay, so does it make sense that what we have done? So now what we would like to do is to say that instead of doing this binary partition, we will use a different shape, so that this large subtree will contribute not log sigma times, but well, fewer times. Okay, so in other words, instead of building a tree of such shape, let me remove this. Okay, we would like to say that maybe it's better to build something like that. There were 8 of them, yeah. And one more, I guess. And there are not enough of them. Yeah, there are not enough of them. So let me add one more. Okay. So instead of using this binary partitioning, so grouping into pairs, pairs of pairs, and so on and so forth, I put this large subtree very close to the root of this binary decomposition. Okay? Like it's almost at the first level. I mean, it's not at the root, but it's very close to the top. So now it will contribute just, well, 2 times, because it's very close to the root. Okay? And the others, well, what's the price that I need to pay? Well, I kind of pushed one of the leaves closer to the root. So some other nodes now have to be deeper in this binary decomposition. Yeah. So this large subtree now is closer to the root, so it pays less. But other small subtrees are deeper, so they pay more. Okay. So there is some balancing. There is some trade-off. The small trees pay more now, but this very large subtree pays less. Okay, makes sense, this intuition, what we want to do? So what do we want to construct? So instead of building this complete binary tree, yeah, so here we construct a complete binary tree where the leaves correspond to the children of V. So assume that the number of children is a power of 2. Yeah? If it's not a power of 2, you just round up, and that's okay. Okay. So what we have constructed? We have constructed a binary tree where leaves correspond to the children of V. And now we are saying that instead of having a complete binary tree, maybe we would like to have some other shape of the tree, so that the leaves, when we read them from left to right, the order from left to right should correspond to the order on the children of V. Yeah, think about all those green edges hanging up from V, and yeah, the order should be the same, left to right. Why it should be the same? Because in the query time, you want to take all children, but not v prime. So we need the children which are on the left to be really on the left in this binary tree. Otherwise, we will get confused and we will not have this nice decomposition. Okay? So we want to build a binary tree where some nodes are closer to the root, and some nodes are further from the root, and there is some balancing. Okay, makes sense what we want to do?
Can you please repeat why shuffle is a real problem? Because even if we have analysis, we need to exclude the I.
Okay, yes, you are right. Here it would not be a problem yet. Okay, you are right. What I said was it was a half truth. So here it would not be a problem, but later we will build those trees on paths, on heavy paths. And on heavy paths, the order is very important because when you reshuffle heavy path, then left to right order will not correspond to top-bottom order. And you want to take a prefix. I mean, on a heavy path, you will take a prefix. And you would like to say that this corresponds to taking a number of leftmost leaves in your binary tree. So you're right. Okay, make sense so far? So now we need to say something about those shapes of the possible shapes. So we want to say something about what is the condition. So we would like to say the following thing. We would like to specify that the leftmost leaf should be at depth something. The second leftmost leaf should be at depth something. So we want to specify an upper bound on the depth of every leaf. And now we would like to have some condition so that we can determine whether such a tree exists. Okay, so we want to specify where, what are the depths of the leaves, and we would like to figure out whether it's possible to arrange them in a tree. Okay, sometimes it's clearly not possible. So maybe you have. So again, here the order is important, but if you forget about the order, there is something called Kraft's inequality. If you took any information, it tells you exactly which shapes can be achieved. Yeah, have you seen something like that? Who has? Okay, so some people have. So there is something that tells you exactly which shapes can be constructed when you don't care about the order of the leaves, and it's a simple inequality. So here the situation is a little bit complex because we will care about left to right order. So we need a stronger version of this inequality which tells you under which condition you can construct a binary tree with specified shapes. Okay, so let me just write down the answer. What's the answer? And then we will think a little bit how to achieve such construction. So I claim the following. So let W doesn't work. So this is a cool trick, I think. One of my favorite tricks. So let's specify weights for every leaf. W1, W2, up to WK. The weight will be just size of the subtree, but at this point it's not important. We just think about the weight. Okay, W1 and WK. Okay, and let capital W denote the sum of all of them. Okay. So now I claim that it's possible to construct a binary tree such that the ith leftmost leaf is at depth at most di, which is log of capital W divided by wi, and probably I need to add +1 just to avoid something weird happening. Okay, so I claim that I can always construct a binary tree such that this is the ith leftmost leaf, and its depth will be di, which is roughly log of the sum divided by his weight. Okay, so that's my claim. I will not show you how to do that. Please think a little bit because it's a cool puzzle. So when you think a little bit, you will see how to prove it. It's not very difficult, but kind of cool. Okay, makes sense? What's the statement that I'm trying to make? So now you can see that the larger the weight is, the closer the leaf will be to the root. Yeah. In particular, if the weight of some leaf is at least half of W, yeah, it will be on the second level. There is big O, so you don't know exactly, but at one of the first constant number of levels. Okay, makes sense? What this statement is supposed to mean? So now let's think about why it's useful in this setting. So it's useful because of the following nice property. When you think about for each v, we arrange the light children using this trick. And Wi is just the size of the subtree. Okay, so we use this binary partitioning, this binary hierarchy, but we set up the weights to be equal to the sizes of the subtrees. Okay? And now I claim the following. It might happen that for some v, for some node v, you will need logarithmic time to, in this binary, in the corresponding structure, the length of the path will be logarithmic. It might happen. But I claim that it cannot happen too often. So it cannot be the case that you will have many nodes v on your path. So again, you have path from u to the root. On that path, you have many light edges, but at most log n. For each such light edge, you pay, well, the depth in the corresponding binary tree. That's how much you pay in the query time, also in the space. But let's think about the query time first. It's the same thing, almost. Okay, so I claim that it cannot happen that you will pay. You see that it could happen at one node v that you will pay log n, right? I mean, there's nothing stopping us from paying log n. But my claim is that it cannot happen everywhere. It cannot happen many times. So it cannot happen that at one node v you will need to traverse a path of depth log n, and then again at its ancestor you will have to pay again that much. Okay, I claim that this follows from this bound on the depth. Okay, so think about it for a minute. Make sense? What we want to?
Can you repeat this?
So again, what we are doing for each node v, such that the next node is such that you follow light edge. You take all the light children of v and you arrange them using this technique. So the depth of v prime will be O of log of the total size of all subtrees divided by the size of the subtree of v prime. That you do for each node v. Now look at all. Okay, so now it might happen that on the path from u to the root you have a light edge, and the depth in the corresponding structure is logarithmic. It could happen. I mean, you don't know. But okay. So that's not so great. But on the other hand, my claim is now that if you look at all light edges on your path, then when you sum up the depths in all of them, you will get something small, not log n times log sigma. Yeah. So with the simple partitioning, the sum of the depths was log n times log sigma, because we had log n structures, and in each of them the depth was log sigma. So that was how much we have paid. And now I claim that now the depths are different in different structures, and I claim that for only u they sum up to something smaller. Okay, makes sense what I'm trying to say? So you have a bunch of operations on your structure, and I'm claiming that some of them might be expensive, but overall they are not so expensive as before, because we did this balancing trick. Okay? Make sense what I'm trying to say? Uh-huh.
So, for example, you have at the beginning you have double. So W0, for example, is the number of, and then you have W1. So you first play log W0 over W1. Then you play something smaller than W1 divided by something. This is this all.
Telescopes. It's the telescoping. You see what's the name? I forgot. Sasha. You see what Sasha means? So each term is log of sum minus log of wi. Yeah. So when you look at this path, So here you had this wi. And here W was sum of all the sizes. Yeah, so you pay. Forget about this +1. This +1 is not important because you have log n terms in your complexity, and each of them adds +1. So you add +1. So it's enough to analyze the sum of those logs. And log of W over W prime is the difference of two logs. Yeah. So here you pay log w minus minus log of wi. Okay? But now how much are you paying further on the path? Well, here you had, w was the total size of all the light children. So here, let's call this w prime I prime. Yeah? So here you pay, the size is at least as much, maybe even more. Yeah? And here you have w prime. So you pay log of w prime minus log of w prime I prime. Okay? And now we say that this cancels with that. Yeah? And when you write down all those steps, they will all cancel out each other, and you will only get one log. Make sense?
But the plus
Log.
will count up to the 2.
Okay, but if it is, for example, it's not. Okay, so a puzzle for you is to show that a tree exists. So you can always proof which is constructive, and there is one which is very constructive. Actually, all of them that I know are constructive, but maybe also there is some non-constructive. So there is, from the proofs, you get a very simple procedure for like one scan over the numbers, and yeah, so that's not a bottleneck in the construction. This trick. So what was the second issue? The second issue was that we you deal with think about a prefix of heavy path. So this is a prefix of heavy path, and you have some other heavy paths above it. Yeah, so this is just one of them. And here you go further somewhere, and your u was some. Last node. To go along this heavy path a little bit, and then instead of following this edge, you want to follow one of those green edges. And you don't care which one, because each of them has the same cost of one. You will introduce one mismatch. Yeah, so for each of them, it's the same. Okay, so you can all those green subtrees, and you can merge them together. Okay, make sense that you can merge them together? Yeah, or so. So for each node of the heavy path, you store one merge. Okay? So that's the first step, but we are still not in a good shape. Do you see why? because you don't know what's the edge that you should change. I mean, you could have a long prefix here, and any of the edges on that prefix might be the edge that you want to change. And you don't want to, for each of them, you would be able to query one merge. Yeah, because as soon as you decide that this is your edge, you query one merge. But yeah, which edge? You do the following: take all those nodes of the heavy path, and again build this binary. It should be animated, but so imagination. You kind of rotate it, yeah, and now you build this binary segment tree on top of that. So this is the heavy path. Here it's attached to the next. This corresponds to the merge. So each leaf corresponds to merge all the green subtrees. Yeah, so I will show this. Okay, and we are almost done. So now we have to say that we where we leave the head. This is a sub. So we look at the corresponding sub. Cover the suffix. Segment. Yeah, so again, fine.
You need to consider the edges between green white edges because they correspond to the sum engine and try result. Right?
So, okay, so maybe that's okay. So the issue is that, so in the end, so you want to take the merge that you store here, and in that the merge is a compacted trie, and in that compacted trie you want to query with the remaining part of your pattern. So each merge should be queried with one string, right? But when you think about what's happening here, so this merge here corresponds to the first 4 nodes, so this, and this. And when you think about it, you are querying those green subtrees with different strings. Yeah. Here you query with a long suffix of the pattern. Here you query with slightly shorter suffix, and so on and so forth. So in each merge, you query with not with the same string, with different things. Okay, and this is an issue. You see what I mean, more or less? There are different remaining suffixes, or there are different prefixes, depending on. Okay, but this is not so bad. You need one more trick. So the trick is that for each of those green subtrees, think about the following. Take all the light edges. So on every light edge, you have some letter, B, C, D, and so on and so forth. And on the heavy edge, you have A. Now, just for concreteness. So I'm saying take all the strings that are in those subtrees, in the green subtrees, and change the corresponding letter from B, C, or D to A. Okay, take all your strings that are connected to this node through a light edge. Yeah, those are just strings. And the next, each of those. The next letters are different I'm saying, I do character in all of them, character A. Okay? See what I mean? By doing that, you are introducing one new one. So instead of modifying the pattern, you modify you. Okay? Like, for each of the see, yeah. So you take all the strings here that are attached to that node, and for each of them you change the next character to C. Okay, and you do that for each heavy edge on the heavy path. So again, here we just don't truncate it. You could truncate them at the beginning of the heavy path. That's fine. But the next character on the heavy path. And if you do that, then you can query with the same pattern. I would kind of consider they don't have as much. Maybe that's a good question. Yeah? So you can do the next task, and that you use up to your budget in the remaining parts. Okay, make sense? Same. And here is so situation, we truncate the suffixes so that they start here. There are a couple of things up to the next node, and we follow the remaining part in this range. Now we can this is one of the strings in the collection. You can truncate it here. So whatever you tap the beginning of the heavy path, you can do that. You don't have to do that, but you can do that. And now modify those strings. You modify the strings in your collection. Okay. How do you do that? Well, look at your string. Leave the heavy path here at that node. So it follows a path labeled with C. And the next edge of the heavy path is A. Okay. So you modify the string. So the next parameter, you replace C with A. Yeah, so for each in a collection that's connected to that node, to this node, you change the next character to A. You need to be careful because now you start modifying strings in your collection, so you need to be careful so that it doesn't break anything, but it will not break anything. Okay, so you modify the strings in your collection. So think about creating more strings. You just create more strings. That's a good way to think about it. So now you will store more strings in your collection. You had n strings, and now after doing this, you will have like n log n strings in your collection. Because you cannot really modify, you have to create a new version of your string.
So when you merge, for example, you have a line in which you change the character.
Yes.
From B to
A. Okay, let me draw the picture slightly differently. So that's the heavy path again. Now there was a substring here. Yeah. Now I change its next character to A. So now it goes along with this heavy path a little bit more, and it will branch later. Okay. And I do that for each node here. I do the same procedure. So now they go along the heavy path a little bit further. Now I have more strings in my collection. Okay, so for each of those nodes, I have the strings that were previously in a light subtree. Yeah, and now I modified those strings and I merge them together. Okay, so for each node, this is some node vi on the heavy path. For each vi, I take all strings. I create. I don't need the old strings. The structure is the old strings correspond to no mismatches. So I'm creating something with one mismatch. So I only put the new strings in the recursively defined structure. So for instance, we have this subtree here, and we have this subtree here. So in both of them, we add this path, and this path. That's what you want. So in all of them, the strings start at the root of the heavy path. We don't truncate them because we want to query with the same remaining suffix of the pattern. Okay, the idea is a little bit clear, not completely unclear. I don't know what's the. I'm happy to discuss later if you have any questions. I think it's cool to speak. Okay, we will do that. Now you have to create more strings. Strings to create many objects because you keep modifying them, and then it means that your space might be like n times log to k, and n was the number of strings. But now maybe it's not the number of strings that's being multiplied by log. You multiply the total length of all strings. But in this way, I think that's not an issue. You don't have to write it down. If you have a string that hasn't obtained one letter, one of your strings, you don't have to write it down again. Usually you can just reuse the same state. You can say that this string is one of those other strings, but the seventh letter is different. But strings is just for to get a picture of what's happening. You don't need to create it. Here on the heavy path, you do the same weight balance. So you don't do it the way pairs and pairs. You balance by weight. So again, it telescopes to one log for one. There are some details. So here it's we want to further optimize the to be local and prefix search. What is operation prefix search? Operation search that you add at the root tree where you get stuck. That's a prefix search. Yeah? So you start at some node in your tree, and you want to follow and find the longest prefix that you can follow, and you want to get where you're stuck. And for larger values of k, you can see that you're doing the same thing over and over again. And then you will be recursively the same thing. You don't have to try that you recursively define again and again. So that depending for efficiency, you implement this prefix search, you will get different complexity. So you could just follow naturally, and you will get something, but it will be multiplied by log to k. So you will get log to k times the length of your pattern. Which maybe not so great. You can do something better. You can process the pattern a little bit and use some predecessor structures to know something like that. Call it automatic. Yeah, you can play a little bit, but I would say this is the main part. Now the open question is, can you do better? No one knows how to do better. So either the data structure nearest closest pair with k as a parameter. So you are given red vectors and blue vectors, and you would like the pair with the having the most k. And I would like to see what the difference of k is. You see that for large k you need n squared, as you need strong specifying hyperlimit. But for small value of k, we have this upper bound, so that gives you roughly n times slope to k. But we don't know whether the precise a good question, but maybe. Okay, fun question. So it's roughly n times log k, roughly the size of the structure. You might need to pay one more log for the construction, but not much more. Because so you need to store the string, and when you store the string, the try, you have a subset of your string, and you want to do doing stuff. So it's one of the strings. So how so you have logarithm now other stuff. Otherwise will be the one a little bit better. It's actually n to the power of k divided by k factorial. So it approaches like n squared when k is around log n. So it feels like maybe the right, I don't know, maybe that's the right complexity. Because it kind of matches the k roughly log n. It roughly matches this n squared, this conditional lower bound of n squared. Log n to the power of k divided by k factorial. Because k factorial is k over e. Again, you will get polynomial, and squared when you choose the constant. So it's kind of more or less.